Let's see. The midterm, what day did I say? I will go confirm that right now. This is why I like to send out announcements. It's so easy to keep track of everything. I've already gotten quite a few of them, and that's good. I think so. Yeah, I'll go over that with you tomorrow. Yeah, the chapter 4, I haven't completely finished writing it yet, but it'll be definitely next week, because you had to do the midterm this week. Okay, so yeah, definitely. Plus, chapter 4 was very, very long, and we really just finished it. So, all right, let me just quickly check my announcements. Yeah, it gets like this sometimes. All right, send me a push. And then I click on the yes, the check button, and it says, sorry, you timed out. Oh, that's right. Yeah. And question 7, oops. Oh, the 14th. Oh, good. All right, that sounds right. Okay, so let's do this. I'll post the chapter 4 problem set tomorrow or tonight. And then this way, something's due every Wednesday, Thursday rather. I think that's a good idea. So this way, chapter 4 problem set due Thursday, the 20. That would be the 21st. Okay. Okay, so the chapter 4 problem set will be due on Thursday, 7/21. Okay, good. All right, so that sounds about right. So that way, this way, the midterm can be due this Thursday without chapter question 7, by the way. And then you can do the chapter 4 problem set for the following week. So right now we're kind of getting deeply into 5, which is more about integration, which in my opinion is more complicated than differentiation. It's just a messier process. And so there's more techniques that we need to learn for the different cases that we might run across. And even then, most of the really complicated ones will probably, you'll see them again in calculus too. Here we're really just opening the doors basically on integration. We're showing you the basic ideas, but the really complicated ones will have to wait till Calc 2. I don't know when you're planning on taking that, but if and when you do, you should make sure you review these notes, because you'll start to forget this stuff very quickly. And yes, and it'll get more involved, that's for sure, especially with the integration. So anyway, so let's get back to where we were, which is chapters 5. The last time, hold on. So here's B. So we did start A, you can tell because of the notes there. And then we did not start B. So we'll probably just get through those 2 tonight. And then we'll probably take a crack at C tomorrow. And I don't know, maybe by the end of the week, we'll take a peek at 6. So, hold on. It's not what I wanted to do. The thing is about the PDF, it's really nice that it works on all platforms, but I can't actually write on it on the screen, which is kind of annoying. So I'm going to go get the PowerPoint version. There we go. Actually, the only reason, all of these notes are written on a PC. You can probably tell by looking at the icons down there on the bottom. And so the problem is that when you write like documents in PowerPoint or Word, whenever there's graphs involved or equations or whatever, when you open them up on a Mac, there's a very real chance that some of it won't be clear or readable, especially symbols. There's something about symbols that tend to go wrong when you switch back and forth between the two platforms. So the way to get around that is to have PDF, because with PDF, you're essentially just taking a picture of what you've done. And so that way it'll look the same on every computer. So, but the drawback is that I can't write on it on the screen. So I post the PDFs, but I use the PowerPoints. So anyway, if you recall, this is we started to do this last time. A is integration. In chapter 4, we briefly were introduced to the concept of the antiderivative, which is essentially just the reverse of the derivative. It's sometimes referred to as integration. I don't know what the correct, if there is even a distinction made between the two, but the words antiderivative and integral are typically used interchangeably. And so what you're basically doing is reversing the process of derivatives. And so you can take some kind of a function. And one of the most important applications of it is that you can calculate the area under that function between two given points. So that's one of the physical applications of it, is the ability to calculate these areas. So anyway, so we're going to, when we look at integration, what we frequently will want to do is calculate the area under a function between two specific points, although it doesn't have to be two real numbers. It could just be the entire real number line as well. You can integrate between negative and positive infinity, although, like I said before, you'll probably not see that until Calc 2. Okay, it gets a little messier when you start dealing with infinity, of course. For our purposes, we're learning the basic concepts and some of the most important rules and getting used to the idea. But if you look in the book, you'll see the list of formulas is quite long for taking these integrals. So, and also in a lot of cases, when you take an integral, the form that it's written in is not very convenient. And so we need to learn several strategies for rewriting them in a form that's more convenient, that's more amenable to being solved with a specific rule. And so we'll see that as we go along. We'll often be in a position where we need to make some small changes just to make sure that we can find a rule that can be applied to that integral. All right, anyway, so here's the graph. And so I just sketched this out. This is y equals x squared. And so if for some reason we needed to know the area between 1 and 5 under that curve, this could represent, for example, the total profits from selling anywhere from 1 to 5 products. What we're doing is we're taking the derivative, but we're calculating the specific value. So whereas up here, we're taking what's called the indefinite integral, which means that you do not need a specific value. You're just trying to calculate a function. If you need to know the exact value of this area, you need to use what's called a definite integral, where the limits of integration here from 1 to 5 are specified. And that way, when you're done, the answer will be a specific constant rather than something like this. Okay, so in one case, all we need is the function. In the other case, we're looking for a specific value. So we're going to see today how exactly to do this. How do you take this integral from 1 to 5 and actually come up with a specific number? What is the area under this curve? Okay, now, also one more thing too, when you solve a definite integral, because you're getting a constant out of it, you don't need this plus c part. That plus c only applies to the indefinite integral. It's a formula plus c, okay, which could be 0, by the way. We don't know what it is. That's what the problem is. Without more information, we can't determine what the constant is. So we just write this as the integral plus the c. Now we can confirm that this is correct by taking the derivative. And of course, the derivative, the constant is just 0. So the constant is actually irrelevant here. It doesn't matter whether it's 3 or negative 50. You'll still get x squared when you take the derivative of this expression. Okay, so anyway, And here, just in the most general possible terms, looking for the area between A and B under this curve, this is how it's done, with the definite integral from A to B of f of x dx. Okay. Now, as far as the integration process is concerned, what you're effectively doing here in order to find this area is that you're constructing a series of rectangles. And there's a couple of different ways of going about this. But no matter what you do, and you can see here in this graph, if the rectangles are very wide, then your total area, the total area of these rectangles will not exactly match the area under this curve. So the strategy here is to basically do this. Start with this right here, create rectangles with some base, let's say 1. And then what you do is you shrink up the bases. So in other words, you're creating progressively more and more rectangles under this curve with progressively smaller bases. And in the limit, as the size of the bases approaches 0, the sum of these rectangles will approach the area under this curve. Now, the integral itself is actually the result of taking the sum of an infinite number of these rectangles. And so with the base of a number that is so small that it's referred to as dx, an infinitesimally small change in x. So in other words, the bases of these rectangles in the limit are so small that they're essentially 0, although they're not exactly 0, they're approaching 0 very closely. And so we end up with the correct area that we need. All right, now, so here we started to briefly review the summation operator idea, because remember, the integral is itself a sum. So it's important to understand how sums work. And so the summation operator is just designed to make things a little simpler for us. It's basically telling us in a very compact way, what are we adding up and how many terms are we adding? So we started with some very simple cases. And by the way, in the book, sometimes it calls it the sigma operator, because it is, after all, nothing but the capital sigma in the Greek alphabet. So sum of xi, that I is an index. Each x is assigned a number from 1 to n. And what happens is the sum, or the symbol, says add all the x's from x1 all the way up to xn. Okay, so I equals 1 to n. The way it's written here indicates that you're including 1, 2, 3, 4, 5, all the way up to n, whatever n happens to be. So we're going to include all the x's in our sum. And by the way, this operator is more flexible than it might appear at first glance. There are ways you can adjust it so that you don't always start with 1. You don't have to finish with n. You don't even have to increase by 1. In fact, you can even go backwards. You can go down if you want. There are ways of doing that. We won't be doing that here. We're going to assume that we start at a specific starting point. We go all the way up to n, one at a time. All right, so I use this quick, simple example. We have 5 temperatures for Minnesota, and each day's temperature is assigned an index. Monday, of course, is 1, Tuesday is 2, etc., all the way up to Friday, which is 5. And then we might be asked to add them up for some reason. And so the formal notation would be the sum of all the x's, x1 through 5. When we add them up, we end up with a 10, and that's all there is to it. So that's a very straightforward idea. We can also expand the range of possibilities here. For example, if we needed the sum of these squared temperatures for some reason, we would express it as the sum of the xi squared, which means x1 squared plus x2 squared all the way up to xn squared. Then you plug in the actual numbers, and you can see what you're doing is you're squaring them first, and only then at the end, when they're all squared, do you add them up. Okay, so you can see that that is going to give us 40. You see this notation a lot in statistics. I don't know if any of you have taken statistics or not. If you're in any kind of a business program, especially for fields like economics and finance, statistics is really like maybe the most important math class you'll take. Now, I'm not saying there's anything wrong with calculus, but you'll use this all the time. But if you're studying physics, then calculus is it. This is what you have to know. This has to be your best friend, basically. You have to know calculus like the back of your hand to be a physicist. So every discipline is different, but in statistics, this notation is used very heavily. So it's good to know this. And by the way, this is also very useful in computer science, because in computer science, you're basically trying to tell the computer what it's supposed to do in the most compact possible way. And so, any language you might happen to be using will probably contain commands that allow you to do exactly what we're seeing here. So any way you look at, at it, this is all very useful. Okay. Even though it might not appear right away, you don't always find out in the beginning when you learn something new what it's used for. But sooner or later, something will come up and you'll say, oh, now I know why these are so useful. Anyway, we can expand this a little further. You can see here where we get x squared, sum of x squares. Here you can see the way this is written. It's the sum itself that's being squared. So therefore here, what we're being told to do is add the numbers first and then square them afterwards. And so instead of getting 40, this time we get 100. Okay. So, and I made sure it's clear at the top that they're not equal to each other. Sometimes you might have to subtract a constant from each term, or there might be other things you might need to do, like add a constant. You might need to calculate a function of x. There's all kinds of possibilities, but here we're subtracting a constant, and then we're squaring the differences. This comes in, again, very helpful in statistics. It's a helpful measure of risk. If you've heard the terms of variance and standard deviation, then you're very familiar with these ideas. And you're just being told, go through each x, subtract k, square the difference, and then add them up. So let's just say that for whatever reason, let's say we took those temperatures in Minnesota and we discovered that the thermometer doesn't work right. It's always giving us temperatures that are 3 degrees too high or something like that. Then you could just subtract 3 from each temperature and presumably get the right number. And then here we also need to square them. So you're subtracting the 3 in each case. Once you've done that, you're squaring the difference. And once you've done that, you can add them up. And so here you end up with 25. Now, it turns out that for certain cases, there are formulas we can use to avoid having to do all this multiplication and addition and squaring and all the rest. There's some specialized cases, which again, this is the kind of thing you might do in a class in something called numerical methods or any kind of a computer science class, where you're actually writing code to generate results. Okay, so I would imagine that many of you already have some computer science background where you have been asked to write code in a language like Python maybe, or Java, I suppose. And, those packages, it used to be that those packages were horribly expensive. Now, in this day and age, a lot of those types of packages can be had for either free or very little money if you're a student, or else your school can get it for you. In fact, there's actually a package that you can buy, which your school may have it. And it is called, and so if you're serious about this stuff, you might want to get your hands on this. The company called Wolfram, they published this software called Mathematica. And now the thing about Mathematica is it's basically, think of it as a professional version of Symbolab. You can see it can do almost any function you can imagine, but it also has these spectacular graphs. And so it is, it is a professional package. Mathematicians would use this to generate results. And, if you're thinking about going down this path towards math as a major, or doing research or doing something quantitative, this is one of those packages you might want to think about getting your hands on, especially if it's free, or at least free while you're in school. Now, of course, it takes a while to learn it. It's not as simple as Symbolab, that's for sure. But the trade-off is that it's much more powerful than Symbolab. As great as Symbolab is, you're not going to get this out of it. Okay. But anyway, so let's get back to this. So here's some other cases. Like if you're trying to add a group of constants, well, then all you have to do is, rather than just adding them up, you can just multiply them by n. Okay. In other words, here, for example, if you have 6 added together 4 times, well, you can add them up if you want to, but you recognize too that all you're doing is multiplying 4 by 6 to come up with 24. By the way, you can actually, when you have a sum involving a constant, you can factor the c out and multiply it at the end. Like here's a simple example. We're adding up 3 5 times and we end up with 15. Here, as I was saying, that I've got c times xi, I can just move the c outside. I can now add up the sum of the x's and at the very end multiply the result by c. I don't need to multiply each x by c and add them up because that could take a while. Instead, I can factor out the c and multiply it by the entire sum. So it's like, imagine if I wanted to take those temperatures I had before and convert them into Celsius or something like that. You could do it this way. So yeah, here's a simple example. The temperature data we just had, for some reason, we want to double them. So there we are. So we had, effectively, you can see that if you multiply them all by 2, you will get the right answer, but there's no point. All you had to do is add them up, come up with 10, and multiply the final result with 2, or by 2. Here's something that should come as a surprise to no one. The sum of, I guess, a sum, a plus b is equal to the separate sums of a and b added together. Same thing with subtraction. Okay. So here, for example, now this one just says that you can take a sum like this and break it up into 2 parts or more if you want to. There's some reason why you need to do this. Let's say here you're adding up AI from I equals 1 to 5. Well, that's equivalent to adding up the first 3 and then the last 2 and adding them up separately. It's probably more likely that you'll want to take the more complicated expression on the right and simplify it to the one on the left. But you never know what kind of information you have access to. There might be cases where it's simpler to do something like this because you already have some of the information and then you don't have to start from the beginning. Now, this is where it gets interesting. And there's more than what I'm showing you here, but these are some of the standard cases. For example, let's say that you're adding, now I, if you notice, I is itself the index. I want to add up I n times. So like if let's say n is 5, adding up I, which means I'm adding up 1, 2, 3, 4, and 5, is going to give me 15. But in this special case, I don't need to bother adding them up because I have this wonderful compact formula. N plus 1 over 2, n of course is the number of terms. So all I have to do is put 5 times 6 over 2, and guess what? There it is. So this can save us a lot of grief if we have a lot of terms. So let me just show you a quick example of this. Suppose instead of 5 terms, we have 100. Now, you can certainly feel free to add them up. But turns out this adds up to 5,050. Now, how do I know that? Because remember, this is n plus 1 over 2, or 100 times 101 over 2 . How do you like that? Now, by the way, there's another even more clever way of doing this. The reason why this formula works is because if you look at these numbers for a second, what you basically have here is, if you notice, if you look at the largest and smallest numbers, they add up to 101, don't they? And then if you look at the second smallest and second largest, they add up to 101. Same thing here. So you know what this means, and we're not going to draw them all, that this contains $50 pairs whose sum is 101. So the total must be 50 times 101, which is 5,050. So this is how you can help yourself remember this. You're actually creating 50 pairs, each with a sum of 101. And so that's why it works. Okay, so in other words, here we have 50, and here we have 101, and there's your 50-50. And this works for any string of consecutive numbers. If there's any gaps in here, that changes everything. But as long as it's a string of consecutive numbers being added together, it doesn't have to start with 1 either. You're always going to get the same result. Interesting. How do you like that? Now, what if I'm interested in adding up not all these i's, but I squared? Well, we're not going to prove this, but it's a little messier. n plus 1, 2n plus 1 over 6. This is the result of adding up all the squared terms. Interesting. So we're going to prove it with an example. So let's say we had just a simple case, the first 5 numbers, we square them and add them up. Like we saw earlier, we had x squared, the summation of the x squared, which means you're adding up the squares. And we have, in this case, 55. Now, why don't we prove that the formula we had earlier does work? n plus 1, 2n plus 1 over 6. Now remember, we had 5 total numbers in our, altogether 5 numbers, 1 through 5. So n is 5, n plus 1 is 6, 2n plus 1 is 11. When you multiply those together, you get 330, you divide it by 6. There you go, 55. Interesting. Now, you do run across people who can do this kind of stuff in their heads. It does happen sometimes. There was actually a movie about that once. God, I wish I could remember the name of it. It was about a mathematician, young mathematician in Oxford in the 30s. And he had this gift for seeing all these relationships between numbers and understanding immediately how they were composed and what interesting features they have. And so apparently it was a constant source. Every time anyone would mention a number, he would have some fascinating fact about it. I don't know how well received that was, but he was a genius, and he was able to do these kinds of things very quickly in his mind. But anyway, now for I cubed, it gets a little messier, of course. N squared, n plus 1 squared over 4. So imagine yourself writing a computer program, and rather than writing code to actually add up a huge number of values that are cubed, you realize, hey, wait a minute, why don't I instead write a line where I just use this formula. It'll be so much faster. And of course, in computer science, speed is the name of the game. You want software to be fast. So this is exactly one of the things you can do to speed things up. In fact, there's an entire branches of computer science where the whole point of it is to come up with more clever strategies for writing the same code, but with less time. Okay, that is one of the areas that they study. And it sort of overlaps with math, as you can imagine. In fact, in most schools, the math and the computer science departments are next to each other because they see them as more or less specializations of each other. I mean, I guess you could think of it that way. Computer science is kind of an offshoot of math. So it stands to reason they'd be housed in the same department or building. Anyway, so here's I cubed. And you can see this time it adds up to 225. And now let's prove that that formula worked. N squared, n plus 1 squared over 4, where n is 5. Oh yeah, what do you know? It works. It always works. Yes, the formula is correct. This is why mathematicians prove things. So you don't have to check every possible case. You know that it works. Once you find the proof, you don't have to worry about it ever again. You're not going to find any examples that are wrong. Oh, now look at this one. Now we had something like this. We're summing up I equals x minus 3 squared. Oh, that's right. We did one just like this, didn't we? Yes, we did. But when we did that, we had to evaluate each term separately and add them up. Here, we want to avoid that. And here's what we're thinking to ourselves. You know what? We have all these wonderful shortcut rules. If there's one of those rules is not this one, though. We did not see a rule like this. So maybe there's a way we could rewrite this expression and break it up into individual pieces, which themselves can be used with our special rules. Well, in this case, the answer is yes, because you can see I minus 3 squared is equal to I squared minus 6I plus 9. You can prove that with FOIL. And now we can break this up into 3 components, as we saw. Hold on one second. Way back here. Oh, no. Oh, this one, yes. Okay, based on this principle, the sum of A plus B we can break it up into the individual sums or differences. So we're doing that here. And also remember I said that you can factor out a constant. Somewhere along the way, I said that. There it is. You can factor out a constant. So here's what we're going to do. To speed things up, we'll break it up into 3 pieces, which we're allowed to do. And then what I'm going to do on top of that is I might be able to simplify it a little, like 6i. There's no rule for 6i, but it doesn't matter because and then this is the constant rule. Remember, we saw that the sum of constants is NC. So we're all set, and we have a rule for I squared. So watch how easy this will be now. So this one, I reminded you that this is the first term. Oh, and by the way, you notice I moved the 6 out here. So for the first term, we use this formula, and it gives us 2,686,700. So the numbers add up very quickly when they're squared like that. Now the I, wait a minute, hold on. What the hell is this thing doing? It was acting very strangely for a minute there. All right, I guess it's done messing around with us. Yeah, so that's done. Now the i's, remember, which implies that minus 6 times that would very simply be minus 6 times n plus 1 over 2. Okay, so we'll do that one next. And yes, it's minus 6 times n and minus n plus 1 over 2. So it's negative 120,600. And then for this last one, the sum of the n's, the 9's, is 9n, because remember, 9 is the constant. And so therefore, it's just 9 times 200, which is 1,800. So now I'm just going to combine them. So I got the three numbers that I had, I combined them properly, and I end up with 2,567,900. So again, I mean, we could have tried to evaluate this for every value from 1 to 200, but it would have taken a very long time compared to this, especially because there's 200 terms. So really, these formulas are really saving us a lot of time here. Now, here's an interesting one. It's I cubed minus I squared for I equals 1 to 6. So we'll break it up into two pieces. And of course, we have formulas for both of these. Now, if there's no formula, then you may still be able to do something with it by rearranging it algebraically. But if there's still no formula at all, then you just have to go ahead and add it up the old-fashioned way, one term at a time. But often we can break up a complicated function and split it up into these simpler terms. And then in these cases, we can use our formulas. So here's our I square formula, 91. Here's our I cube formula, which is 441. And then we'll subtract one from the other, and we'll be all set. $350. All right, so now we've had a good background in summation. Now we're going to dive into the mysteries of the integral. We're going to try to understand what exactly is this thing? What are we doing with an integral? All right, so we'll start out with some abstract ideas, and then we'll work our way up to some specific examples, as we always do. What we're trying to do is approximate the area under a curve. Now, as is so often the case, we're going to assume that the function is continuous. If it's not, well, that changes everything, because derivatives may not be necessarily defined at these discontinuous points. But if the function is nice and continuous, and we're looking at focusing our attention over an interval from A to B, including A and B, it's a closed interval, we're going to calculate the area under that curve as a sum of rectangles, in spite of the fact that the curve itself is not necessarily straight. So you might look at this and say, wow, any rectangles we draw here are going to lead to a lot of inaccuracies. And that would be true if the sizes of the rectangles were fairly large. In fact, the larger the rectangles, the worse the approximation will be. But if we can construct rectangles with very small widths or bases, then as we shrink up the rectangles, the areas will converge to the area under this curve. All right, so now here's what we're going to do. We're going to split this thing up. Let's see. So basically, we have to decide how far these rectangles should be apart. Let's say that this A is 2 and this B is 6. We decide to break this up into 8 equal pieces. Well, all right, I'm doing my best. Anyway, now here's the part that's tricky. The rectangles themselves, what you're seeing there, those are not rectangles. The tops are not flat. Or I should say the top is not parallel to the bottom. So we're going to see in a minute that we have to make a decision. Where do we construct the tops of these rectangles? Suppose I choose to do it like this. So you can see that here we're understating the true value of the area, and over here we're overstating it. So those cancel each other out to a certain degree, but you can see that the approximation isn't really that good. But if we chose rectangles that were a little closer to each other, really close, well, you can probably visualize that the area is getting closer and closer to the real area. So each rectangle has a height of f of x evaluated at this point. We'll call this xi minus 1 and xi. So the difference between these two is often referred to as delta x. So the i's will run across the entire interval here from one. Usually they start at 0. They'll go from 0 up to n. And so the difference between two consecutive x's is called delta x. It's the same for each rectangle. This is the height, this is the base or the width. And the area, of course, of a rectangle is the base times the height. And so that's what we're trying to accomplish. Okay, so here's what they're going to have us do. So the gaps between these let's say that's our function. So this is delta x, this is delta x, delta x, delta x, delta x. And so this equals, like, for example, this one is x5 minus x4. This one is x2 minus x1. So it's always xi minus the previous I rather. Yeah, that's right. I minus 1. So because we have 5 rectangles here, that means that each delta x is equal to, let's say this is A and this is B. So in other words, what we're trying to capture here is that B minus A is the total width of this area. When you divide it by the number of rectangles, the size of each delta x is that ratio. And for any x that we need to know, for example, if we need to know where x3 is, it's x0 plus I times, in this case, 3, the change in x. All right. So yes, this is all very bizarre and abstract. So don't worry, you'll only need to do this deal with this once or twice when we try to calculate integrals using this definition. Then we can go ahead and use the rules. Just like with the derivatives, rather, you're required to solve for the derivatives using the limit definition, and then you're allowed to use the rules. Okay, so now here's the interesting challenge. Actually, let me draw that a little differently. We need the rectangles have to have a flat top. They can't be curvy or anything like that. So what we have to do is approach this area in one of two ways. I'm trying to draw it myself, and I'm having the problem here. Let's try this. Oh, Jesus. Oh, that's better. So what I'm trying to get at here is that in order to describe the width of the height of the rectangle, if you notice in the top case, the height of the rectangle is right here. This point is x1, f of x1. So the height of the rectangle is f of x1. But we could have done this. What if I chose to use x2 as the height of my rectangle? Oh, now that's different, isn't it? This point is x2, comma, f of x2. And so the height is f of x2. So for each of these intervals, we're going to choose either, or we're going to call, and by the way, before I go any further, this is called, for this interval, this is the left endpoint. And this is the right endpoint. Each interval has a right and a left endpoint. So if you notice, I can use either endpoint to represent the height of my curve, of my rectangle rather. And you can see it makes a difference which one I pick. In the top one, I use the left endpoint, and my height of that rectangle is f of x1. In the bottom case, I chose the right endpoint, and as a result, the height is a little higher. It's f of x2. So when we do this area under the curve calculation, we have to pick one or the other. We can't mix and match. In other words, you're either going to have always the left endpoint or always the right endpoint. So we'll do the first one, the left endpoint approximation first, the one you're seeing on the top. Okay, notice for each interval, the left endpoint will represent the height of the rectangle. As long as we're consistent and always do it the same way, we should get good results. Okay, but like I said, you can't just arbitrarily choose. Sometimes it's the left, sometimes it's the right. It's always one or the other. So we'll start with the case of the left endpoint approximation. All right, so let's look at this. And yeah, so you notice what's happening here. This is I minus 1. This is the left endpoint. This is the right endpoint. Whatever I is, the one to the left of it is I minus 1. So we're going to add those up. And here's the formula. The area is approximately what we're going to call Ln. Now, one more thing. Regardless of which approach we take, this horizontal distance will always be delta x. Okay, so the base of each of these rectangles is always delta x. The height is what's different from one approach to the next. But of course, the area of a rectangle is always equal to the base times the height. So with the first approach, the heights of the rectangles look like this. Okay. Now there's a graph in the next page from the book, so you can see it more clearly. But we're always starting, this is always the left endpoint. So that means there's the curve. We start at x0, x1, x2, and let's say x3. And these are our rectangles. Now the delta x's are supposed to be the same. So the height of the curve, or the rectangle, I should say, at x0 is here. This is the height at x1 all the way out to n minus 1. So what you're doing here is adding up a bunch of areas. Call this the area of rectangle 1. Area of rectangle 2. And then this is the area of rectangle n. And this summation represents all of those, and that is the area approximately. You notice they're using the approximation sign. So that ln is there to remind us that this sum was calculated by looking at the left endpoints, L for left. Ooh, it's getting very complicated, isn't it? So yeah, I mean, this is just a better look at what we've actually been doing. You can see that the left endpoints determine the heights of these rectangles. Okay. And we're going to add them up, of course, to come up with our approximate area under this curve. Now, of course, if we can do this with the left endpoints, we can do the same thing with the right endpoints. And you can probably guess how that's going to work. Well, it means that we're going to use always the right endpoints to calculate the heights of these rectangles. So for each subinterval, it's the xi, not the xi minus 1, the xi that determines the heights of these rectangles. We're still adding up the same number of rectangles. The areas are the same. And you notice here, then we call this the right sum, because we're doing this with the right endpoints. Now, in the limit, you can probably imagine the limit as delta x goes to 0. And that A is the area under the curve. So in the limit, as we shrink up the rectangles so that the bases are converging to 0, there'll be an infinite number of rectangles whose total sum is exactly the same as the area under that curve. And it will no longer matter if we're approaching from the right or the left, or I'm not approaching from the right or the left, if we're using the right sum or the left sum. In the beginning, when the delta x's are small, but not zero, there can be differences between Rn and Ln. Usually Rn, well, I shouldn't say that. Depending on the function, one could be greater than the other. They're not normally equal, but they will get closer and closer as the size of the rectangle shrinks. All right. So yes, here you are. This is what we mean by the right endpoints. And you can see that the picture is different, isn't it? As a matter of fact, I tell you what I'm going to do. I'd like you to be able to see them side by side. I think we can just about pull it off. Yeah, I mean, for the same set of data, you can see the rectangles are very different, aren't they? Over here, it looks like we're probably understating the true area. That's just because of the function. It doesn't always work out this way. Because the bars tend to be under. You see these white gaps here. But over here, you can see they tend to be poking up above the curve. So here it looks like we're overstating the actual area that we need. So anyway, so here we have a numerical example of this. We're going to start with something simple. F of x is x squared over 2. And we're going to look at the area between 0 and 3. And we're going to approximate that area using both approaches, the left endpoint and the right endpoint. Okay. I don't think there were any pictures. Oh, you know what I should have done? I'm going to go to Symbolab right now. Good old reliable Symbolab. Just to get a look at the graph. Okay, here it is. So we're going to be looking at the area between 0 and 3. And we're going to do it with rectangles rather, that have a width of 0.5. So for the left endpoint approach, let's see, where's the half? So we'll start, now remember it's the left, ooh, that means this is a straight line. And then here we have the next one. So you can see it's going to be too low. But what we want to do is see how this is actually being calculated. So the heights are what we're really interested in. We know that the bases of each one of these, each delta x is 0.5, any way you look at it. So in other words, for the first one, the height is f of 0. This one, it's f of a half. This one, it's f of 1. Oh, you know what I just realized? I missed one of them. Oops. Okay, sorry about that. So this one has a height of f 1.1. So basically the area here is going to be so it's going to be, we're going to take all three of these. And then the last one is f of 2.5. And just remember too, the function itself is x squared over 2. And each delta is 0.5. So with that information in hand, we can go through and multiply each height by each weight and add them up. Okay. So I'm going to do that right here. Here's the general expression. Here's the actual numbers. And they add up to a grand total of 3.4375. Okay, so I'm going to make a note of that. Ln, which is what these are called. Ln is the sum of these. 3.4375. And you can see visually that it's too small. None of the rectangles are taller than the curve. All of them are actually shorter. So they cannot, this can't be right. By the way, the book has its own version of this. And you can see that the one we just did is the one on the left. And yes, it is seriously understating the true value of this function under the curve. So what do we do about it? Why don't we try the right endpoint approach? Well, you can see on the right that that's going to give us too much. Okay. So how would that work? Let's draw this graph again. So what's different here is that it's always the right endpoint that determines the height. So there's still 6 rectangles, any way you look at it. But we overstated it, didn't we? Yeah. So this time it turns out, and based on the same calculations, we have 5.6875. So we know it's got to be somewhere between the two of them. But how do we find it out? Okay, so this is where the limits come in. And this is where we actually start to do integration. So what we have to do is try it again. Yeah, it's somewhere in between. We're going to try it again with smaller delta x's. The approximation can be improved by reducing the width of the rectangles, which means increasing the number of rectangles. Now, you could certainly write a program to do this if you felt so inclined, but in the limit, as the width approaches 0, the total area of the rectangles approaches the area under the curve. So rather than doing a bunch of calculations, what we can do instead is actually take an integral. So this is actually saving us a lot of time. When we calculate an integral, it's preventing us from having to solve for a huge number of rectangles and add them up. So what we're going to do now is see how this is done. But since it's definitely break time. So when we get back, what we're going to do is work through an example where we can see the connection between limits and integrals. And then we're going to formally introduce the concept of the definite integral, where we're looking for a specific value rather than a function. Okay, so we'll save this for after the break when you have time to get some caffeine or something, because, it's a little tricky. So, all right, anyway, we'll stop for a bit as we always do. And then when we get back, we'll carry on with our Riemann sums, and then we'll tie this together with integration. And then we'll learn the rules or how definite integrals are different from indefinite integrals. All right, I'll see you in a bit. Okay. All right, so now we're going to introduce something called the Riemann sums. Now, of course, Riemann is a mathematician. Among many things, he did interesting work in the area of complex numbers and division by zero even. And so he's a very famous mathematician. And so this is basically a compromise between, what we're about to do here is basically a compromise between the left endpoint method and the right endpoint method. With the Riemann sums, we have the flexibility to choose something other than the left or right endpoint when we construct our rectangles. And so for some cases, that might speed things up a bit and make it quicker and easier to converge to the correct solution. So we're going to write this as, instead of the usual f of x dx, or f of x minus x I minus 1, that little asterisk is meant to indicate that this is a Riemann sum. This is a, let's see, if we drew, let's say, a rectangle, let's say that this time around, we're going to construct our rectangles from the midpoints. Oh, well, I'm not drawing it very well, am I? No. Okay. Let's just say, but the idea here is that with the Riemann integrals, or the Riemann sums rather, the height of the rectangle does not have to come from, oh, I know what I did wrong. Does not have to come from either endpoint. It can come from any point within that interval. Let's see if I can take another stab at that drawing. So the midpoint would be right about here. Oh, this is awful. All right. Well, you have to try to get, so in other words, the height equals the midpoint. The midpoint determines the height. That's what I'm trying to get at here. That would be one possible way that we could have a Riemann sum that is different from the left and the right endpoint methods. Anyway, so it turns out that with these Riemann sums, and the Riemann sums can be used based on the left or right endpoint. It's just that they don't have to be. But the formal proof of what an integral is depends on these Riemann sums. And so the limit, as n goes to infinity. Now, here what we're taking the limit of is the number of rectangles. So what that means then is that in order to have more rectangles between points A and B, the only way that can happen is if the widths of these rectangles are getting smaller. So as n goes to infinity, delta x is going to 0. And the number of rectangles is increasing and approaching infinity, and therefore the widths of the delta x's have to be shrinking up to 0. In the limit, we end up with exactly the right area. And so that forms basically the formal definition. This is how we derive the definition of the definite integral. And again, remember, the definite integral is the one that is defined over a specific range of values so that the result is a constant rather than simply a function. Anyway, so this is how it's actually written. So if you notice from here, all of this is simply the area under the curve. So there it is. So if this is your function, this is A, this is B. This area is obtained by taking the integral from A to B of f of x. Now, by the way, if you notice, it's written this way because remember, this means there's an infinite number of rectangles, each with height f of x. Now the dx, as delta x shrinks, it gets very, very small, and it reaches, this is what's called a differential. And it's a tiny change in x. It's not zero, but it's a very small change. So delta dx is meant to represent an infinitesimally small width for your rectangles. So ultimately, the bottom line is the area under this curve comes from the integral evaluated from the points a to b. And also, if f of x is continuous, then it's guaranteed to have an integral over that interval. Okay, it must exist. All right, now we're going to do one simple example with the Riemann sums. We're actually going to choose the right endpoint method because it's simple, but this is the function that we're integrating. We're interested in the area between 0 and 2. Okay, so what do we do here? Well, let's just say that the width of the function of delta x, as we saw before, b minus a over n, where n is the number of rectangles. Because we've chosen the interval 0 to 2, this reduces to 2 over n. Now, we saw this earlier. If this is x0, and this is x1, and let's say this is x2, let's say that the delta x is 1. That means that x2 is x0 plus 2 times delta x, or just x0 plus 2. So that's what this is. We saw that earlier. No matter which x we choose, this relationship always holds. So if we define delta x as being 2 over n, that means that each x has a value of 2i over n. Now we're going to use that information to construct a Riemann sum using the right endpoint method. Okay. Let's see. I don't think I. Oh boy. It looks like I did not create a graph for this. So since the function is x squared, each x is equal to 2i over n. So that implies that the height here is 4i squared over n squared. So we have the sum of these terms. Now, remember before we showed all these different cases. If we rearrange this algebraically, we may be able to come up with a specific solution. Let's see. So if you multiply those out, you'll get the sum of the 8i squares over n cubed. So this is what we want to do. Let's move these outside because these are constants. This we already know. Okay, well, that helps. So we plug it in. Now we're just going to do some algebra. A lot of messy algebra. So this is the result of adding up all those triangles. And as we allow the number, now remember, n determines the base of each of these rectangles. As we allow n to grow in the limit, we're going to take the limit of this expression, and now we can just use our normal limit techniques from chapter 2. We know how to do these. We break them into 3 pieces. Well, this first one is clearly equal to just the constant. The limit of any constant is just equal to the constant. Now here, remember the limit as n goes to infinity is 0 because n is getting extremely large, so that ratio is getting extremely small. Here we had a constant 4, which we could have moved outside, I guess. It's still 0. And the same thing with this one, except now it's approaching 0 even faster because we have n squared in the denominator. So the limit n goes to infinity of 1 over n to any power other than 0 is just 0. So we end up with 8/3 plus 0 plus 0, so that equals 8/3. That's the formal definition. So what we're going to do now is start using the rules, because we don't want to do this every time. This is obviously a major ordeal to set up these Riemann sums, but this is the formal way of doing this. The informal way is to use the rules that we introduced in chapter 4. Okay, the rules will make things a lot simpler, but there does eventually come a point where we may have cases where the rules don't seem to apply, and yet if we apply some algebraic rearrangement, we might be able to set up our integrals so that we can directly apply the rules. All right, so let's see how that works. Let me just do one thing here. Got to be careful with these. When I do more writing, what's today, the 11th? The more writing I have in there, the more bulkier it is. And sometimes I run out of space. And that's always ugly. All right, so that's the background. Now we can look at some rules. I like the rules. Whoops, that's not it. So the purpose of this section is to show us how to evaluate definite integrals. Up to this point, we've essentially focused all of our attention on the indefinite integrals. Now, what's interesting here, though, is that up to this point, if you notice in all of our examples, a typical case looks something like this. And so we were asked to figure out the area under the curve. Now, here's the tricky part. What happens now? Suppose I'm interested in this area. Uh-oh. Guess what? This area is positive. And this area is considered to be negative because it's underneath the horizontal or x-axis. So we have to be careful with these cases because it matters what the function looks like. The approach can change depending on whether or not the entire function is above the horizontal axis or if any of it dips below the horizontal axis, because then you start getting areas that are considered to be negative. Okay, the rectangles are facing down here on the right, and that means we have in principle a negative area. And in fact, if the two sides are exactly the same, the entire integral will equal 0. So when we have something like this, the Riemann sum is going to be defined in terms of the sum of the rectangles above the x-axis minus the ones below the x-axis. Now here you can see I did a better job drawing it. You can see the rectangles above and the ones below may not perfectly offset each other, but they're going to be very close. So the total area under this curve is actually going to be very close to 0. All right. It's like, oh, here's an example from the book. Let's say we're interested in the area between 0 and 2. Well, again, you can see we're using the rectangles to figure this out. And, well, they may very well add up to 0, or at least it'll be close. So we're going to define the ones that are positive. This will be defined as area 1, and this will be area 2. And so the Riemann sum is going to be the difference between the two. Positive area minus the negative. Now, of course, it isn't really, there's no such thing as a negative area. When we say negative in this context, it means area below the curve. The A2 is actually a positive number as well. But in terms of the integral, we're defining that as a negative area. So the net area, which is what we're after, is the difference between the two, and it could actually be negative. All right, and so here's another picture of that. You can see what are we aiming for. If we're only interested in the area between 0 and 2, we're going to wind up with what's called A1 minus A2, is formally known as the net signed area. And when we calculate the definite integral over this range, this is what we're going to wind up with. Okay, so remember the two endpoints are 0 and 2. And that's how it works. All right, now we're ready for an actual example of this. So suppose we have a simple function, f of x equals 2x. It's a simple straight line, and we're interested in the area between the function and the x-axis over the interval from negative to positive 3. Well, what does that look like? Okay, so again, we're looking at the area between negative and positive 3. This is the function. F of x equals 2x. Now, you can see in this case, in terms of geometry, area 1 is a triangle. And you know the area of a triangle is 1/2 the base times the height. The base is right here. This is 3. The height is 6. Because this is the point x f of x is 3 comma 6. Okay, so 1/2, 3 times 6 is 9. Now down here it's the same. It's just that you've got, in terms of geometry, again, even though you've got 0, this is -6. The base is still +3. This is, triangle can't have a negative base, and the height, you can think of it as 0 minus -6. It's still 6. So A2 is also 9. Now, the thing is, you would think that they might add them up. No, because we're looking at the area under this curve with respect to the horizontal axis. The actual area, or Riemann sum, will be A1 minus A2. A1 is first because it is the positive. It's the part that rises above the x-axis. It's actually going to be 0. Formally, the definite integral over that range is going to be 0. Not 18, but 0, because half of it is below the horizontal axis. Okay, now, if you do this more formally with the integrals, what you're doing is you're integrating 2x dx and over the interval -3 to +3. And we're going to see later on, very soon as a matter of fact, the way you actually evaluate this integral. But for this example, what we're really interested in is how do you do this with geometry? And in fact, you end up with 0, just as we showed. So again, remember, this is referred to as the net signed area. And this equals the Riemann sum, which in turn equals the definite integral over that range. So we can actually now define the definite integral in terms of those areas. Okay, so the book has a very formal definition here. Let's take a look at it. Suppose f of x is an integrable function. Now, of course, it's understood that there must be an integral defined in that function over that interval from a to b, closed interval. And no matter what the shape looks like, whatever's above the x-axis is defined as A1. And the part below is A2. All right, and so these are the endpoints. So whatever the function is, the definite integral is simply equal to the difference between the two. Oops. And that means that this, remember the one above the curve is always A1. This number could be 0, it could be positive, and it could be negative. It could be any of those. But remember, we're thinking in terms of the net area, not the total. And that's why it could be 0, or it could even be negative. Now, the actual total area, if you, let's say you were a sculptor and you had to build this thing, the total amount of area you're covering is A1 plus A2. Okay, but in terms of the integral, that's not what we're interested in here. So in this case, that would have been 9 plus 9, which is 18. All right, so finally, at long last, we get to introduce some properties of this definite integral, and then we get to do some examples based on rules. Okay, so all this background is important for us to understand what we're doing, but I think you'll agree that the rules are very simple to use. So first things first, what happens if we're trying to evaluate this thing at a single point? Good question. So the area of this line is 0 by definition. So in other words, you see how it goes from A to A, no matter what this function is, that has an area of 0. You might remember from high school geometry that the area of a line is 0 because it has no base, no width, I mean. Not a rectangle. This is not a rectangle. It is a straight line, or I guess you could say a line segment. Now, here's some interesting results. This first one might surprise you. The second and the third one should not be a surprise at all. Here you're just adding together two integrals. You can split them up into two pieces as long as they have the same upper and lower limits. And here you're subtracting. So that should be no surprise to anyone. But this is the weird one. The area between A and B is the negative of the area between B and A. And that's an important property. We'll see that later on when we're trying to simplify some of our results. All right, what else do we need to know here? Well, constants, like we've seen all along, whenever there's a constant involved, we can often factor it out, which we did here. And the advantage of doing that is that it might be easier to recognize when there's a rule that we can apply in here. And then look at this one. Now, we saw something similar to this with the summations. And by the way, don't forget, these integrals are just nothing but infinite sums. So the properties that apply to that summation operator applies here too. So remember, we saw something like this. We can break it up into pieces. A to B could be broken up into A to C, and then C to B. It means the same thing. All right, now, before we do any examples, what I'd like to do is go back and revisit 4D, where we had our first introduction to these rules of integration. We got a taste of them. Just a quick reminder of what we've already seen before. There's one in particular that we'll see quite regularly. This one. Sometimes it's called the power rule. I think you'll run into this very, very frequently. Remember this x to the n power dx. We integrate that, and we end up with x to the n plus 1 over n plus 1. Of course, with indefinite integrals like we have here, we always need this plus c. The only time this doesn't work is when x equals -1, because then we have a separate case. That's going to show up quite regularly. What else do we do here? Oh, the constant, yeah, we'll just move that out. And, oh, yeah, these guys, yes. By the way, you might recognize this one. This is that case. In other words, 1 over x, oops, I did the wrong thing, at -1. This is x to the -1. So in other words, this rule applies everywhere except 1 over x, because x is, in fact, x to the -1. So in other words, this rule, for any x to the n, you could come up with except this one. You have your x to the n plus 1 over n plus 1. In this one case, though, you end up with a natural log. So that's why we always have to say here, n is not -1, because if it is, you wind up with this special case. And of course, one of our favorite ones, e to the x, the integral of e to the x is just e to the x, plus c, of course. So those are the ones we already know. And of course, in all these cases, we are still working with indefinite integrals. We were not looking for a specific result, just the functional form plus the constant. And so, oh, and of course, we had some trig ones too. We may need some of these. The integral of sine x is negative cosine x plus c, and the integral of cosine x is sine x plus c. By the way, if you're not sure, you can go ahead and if you take the derivative here, you'll see that you will in fact wind up back to sine x, and here you'll end up back here. So in other words, you can always try to confirm these by taking the derivative of the result and seeing if it brings you back to the original integral. All right, well, anyway, so with that refresher of our memory, let's try this one. And you can see it's a polynomial, but what's happening here is that you're evaluating it between these 2 points. This is all we care about. Now, I think it's time to grab a function, a graph from from Symbolab. Let's take a quick look at that. So we can visualize what we're trying to find. So it was negative 3x cubed plus 2x plus 2. Okay, so we're interested in this over the interval from -2 to 1. So let me grab a picture of this. All right, looks like this is -2. And we're watching it from -2 up to 1. This is what we're trying to estimate. Okay, so let's see, how does that work? Oh, okay. So for now, we're going to just settle for seeing the functional form. We'll come back to this later on and we'll solve for it directly. I'd forgotten that there's 1 or 2 more things we want to cover before we do that. But so what I did was I moved the -3 here. 2 is here. Actually, you know what? I think we can do this. I know the book stopped right here, but I want to carry it on to the next step because we do know the right rules. All we need is the power rule. All right, so what about this first one? So here's what we're going to do. Here, I might as well introduce this notation now. Once we've actually evaluated the integral, which clearly will be x to the fourth over 4, what we're going to do is write it like this. Now, this is meant to indicate that we've already solved the actual integral, but we haven't evaluated it between 1 and -2. So some books just use a straight line over here. Some use the brackets. For this one, we'll have 2 x squared over 2. And this one is just simply 2x. Oh boy, running out of space. All right, so let's do it here. Now, these brackets have a very specific meaning. What we have to do now is evaluate the function here and subtract the evaluation of the function here within the brackets. So it's shorthand notation for saying, all right, evaluate this function at 1, do the same for -2, and then subtract them. Now here we don't need this. This is just x squared. So we'll have 1 squared minus -2 squared. And then here we'll have 2 times 1 minus -2. So whatever this catastrophe is, that will be our result. Now, the book is taking their sweet time about introducing this. I know why, because there's a couple of important theorems that we need to look at, but I just want to give you some sort of advanced notice that this is how we calculate these definite integrals. All right, so this is -3 times minus 15 over 4 plus -3 plus 6. All right, so what does that add up to? Okay, that should do it. Unless I've made a dumb mistake somewhere. No. All right, and we can prove it with the Symbolab. Let's go back there and evaluate this with Symbolab and see what it says. So it definitely has this capability. If you're, there it is right here. You use this as your starting point. It needs the lower and the upper limits of integration. And then you put in the function, which in this case was, oh, it's the same one I had just before, minus 3x cubed plus 2x plus 2. Oops, what did I do? But don't forget the dx. I don't know how it'll react if you leave it out. T704 right there. Nice. Okay. So in other words, that tells me this area right here. So that, I mean, this is, you know, getting ahead of ourselves a little, but you start out by breaking it up into pieces, you apply the rules. And in the book, they just stopped right here with this example, but I just wanted to see what you're actually going to do next. And we'll come back to this again, but they want to throw some new information in here before they actually allow you to do this. But you can see it's really not that difficult. Okay, so what they want to do is introduce a very important result in calculus, and it's actually called the fundamental theorem of calculus. And you would think that this is the most important thing in calculus, and it is, I suppose, but what it essentially does is it tells us how to calculate a definite integral. I don't know how it got to be the fundamental theorem of calculus. That seems to suggest it's the most important result in calculus. I don't know if that's true or not, but that's what it's called. So, and we'll get to that. We'll introduce it and explain it, but eventually what we're going to end up doing is a lot of examples of definite integrals doing exactly what we just did. And then we'll introduce some techniques that will help us solve for more complicated cases. So anyway, so it's after 9. I guess we better stop here, and we'll pick it up from there. And we'll carry on with our discussion about definite integrals. Along the way, we'll learn some new important theorems and some more important techniques for solving integrals. Okay, you're welcome. I'll see you tomorrow. All right, see you later.